Necesito mucho más práctica hablar español. Nunca estudio. My second apology is that I had which way should I be pointing this? Okay. You've already seen today some of the ways in which you and your colleagues are rewriting the textbooks on planetary astrophysics. I was, until recently, rewriting my talk, and so I have to apologize that things are done very hastily. It's a very busy time of the year, and you'll see some of the reasons why I was particularly busy this past week. I'm going to tell you about results from space telescopes. And when you ask members of the public about space telescopes, this is usually the one they think of. El Telescopio Especial de los Estados Unidos, the Hubble. We had a big poster of it at the welcome reception last night in the hotel. Let me introduce you to Canada's first space telescope. There it is. It is called MOST, which stands for Microvariability and Oscillations of Stars. Sorry, I'm not used to using one of these types of microphones. Can we not? No. Oh well, if you can, I'll try to hold it the right distance. Normally, no one accuses me of being too quiet, so in a room this size, I just shout, but MOST stands for Microvariability and Oscillations of Stars, and microvariabilité et oscillation stellaire, so be grateful. I could be giving this talk in French, not in English. But because of this comparison with the Hubble Space Telescope, we have nicknamed ours the Humble Space Telescope. And for those of you that don't get the English joke, go home and get a Spanish-English dictionary and you will laugh and laugh tonight. Also, our telescope resembles a famous celebrity, and so sometimes we call it Space Telescope SquarePants. MOST is a photometer, a light meter in space, and it is capable of seeing changes in starlight as small as 1 part per million, 1/10,000th of a percent. That's a hard number even for astronomers sometimes to comprehend. I was trying to explain that last night at the reception to a few people. And if astronomers have a hard time with it, you can bet that government officials that you're approaching to fund your project also have that problem. So I had to come up with a way to explain how sensitive is MOST. What's it like to see a change in brightness in flux of 1 part in a million? Well, imagine going to New York City, looking at the Empire State Building at night. All of the lights are on, all of the window shades, the office blinds are completely open. You can make the Empire State Building fainter by 1 part per million by having one person stand at one window and pull down one window shade by 3 centimeters. And if you have that person move it up and down by 3 centimeters, you will make the Empire State Building oscillate in brightness by 1 part per million. That's the kind of job we wouldn't even give to a graduate student. Here is MOST, me in the clean room in my bunny suit beside the satellite. It is the size and mass of a suitcase. And with a total budget of $7 million US at the time, about $10 million Canadian. And so we're the Walmart of space telescopes. We're the suburbia of space telescopes. Nobody ever did this kind of frontline astronomy from a microsatellite with such low inertia because nobody could point one before. Pointing a microsat is like trying to look at a star with a telescope on a boat on a very violent sea. Actually, it's more like trying to do it with binoculars. And a Canadian company, now known as Microsat Systems Canada Incorporated, developed the technology that allowed us to improve the pointing with such a small satellite by a factor of about 8,000 times. And that's what made the science I'm going to tell you about possible. That's the satellite. I had a brief introduction. Let me reintroduce myself as the mission scientist. The reason I'm showing this slide is to emphasize that the most satellite actually weighs more than I do, or I weigh more than it does, I should say, and I'm only giving you a lower limit to my mass of 54 kilos, 504 kilos. 54. 504 algún día. The instrument at the heart of it is a Maksutov telescope. The aperture only 15 centimetros, 15 centimeters, the size of one of the dessert plates that we had for almuerzo today. Here's the design, and for the theoreticians in the audience, the light comes in here and it comes out there. That's pretty much all you need to know. There are no moving parts in our instrument. That's part of what increased the reliability and reduced the cost. We have no focusing knob. We maintain focus because all of the mechanical parts are selected with different coefficients of thermal expansion. So as the temperature changes, certain parts expand, other parts contract, and keep our point spread function within our optical tolerances. We have no shutter. We end our exposures by doing a rapid frame transfer into a buffer on CCDs that were manufactured by E2V, formerly Marconi. We look through a single custom filter, which happens to span about the range of visible light, and has a throughput about 2.5 times the standard Johnson V filter. You might have noticed, if you look carefully in that optical design, that there's something called a Fabry microlens array. And that is one of the things that's relatively unique about most. But the idea is not unique. I took it from my experience doing photoelectric photometry in the ground, including many nights atop San Pedro Martir. Here's one of those nights with my former PhD student, now a member of the Kepler team, Jason Rowe. And a photoelectric photometer has a Fabry lens which projects a pupil image of the telescope onto the cathode of the phototube. And what we do is we use a Fabry microlens to project an image of the pupil of our telescope onto the CCD. And so we produce things that look like donuts, very typically Canadian, except this is a donut that illuminates about 1,500 pixels for each bright star. And our original mission was supposed to be 1 year long, to observe 10 stars in this way. We're approaching our 10th birthday in orbit, and we've added 2 new ways of collecting photometry, and so now we're at above 4,000 stars observed in different modes, from roughly the brightest stars in the night sky down to about 14th magnitude. Here's SpongeBob on his head, awaiting launch atop the 3rd stage of the rocket. The Russians would call it a rokot, which is the Russian word for thunder, roar, noise, racket, appropriate name for a rocket. American military strategists would call it an SS-19 Stiletto, because this is a former Soviet nuclear missile, intercontinental ballistic missile. I actually found a weapon of mass destruction and got rid of it peacefully. So the score at last count is Jaymie 1, George W 0. And here's the launch. We should be grateful it was never used for its original purpose, because it worked beautifully from the military Plesetsk Cosmodrome in northern Russia, just on the Arctic Circle. Now, a successful launch doesn't mean a successful mission. We had to wait 7 hours before our satellite passed over one of our operating ground stations to confirm that SpongeBob had survived his rough ride into space. This is launch plus 7 hours. This is launch plus 7 hours plus 1 nanosecond. This is launch plus 12 hours. And right now you're seeing me at launch plus almost 10 years. We were put into a special orbit, pole over pole, but sun synchronous, so that we always stay over the dividing line between day and night, the terminator of the Earth. And from that vantage point, we can basically, as most orbits around the Earth, you can imagine a cone radiating from the telescope that rolls over the upper atmosphere of the planet, and any star that's within that cone is never eclipsed by the Earth during the most orbit. Our continuous viewing zone is a cone about 54 degrees wide, and it allows us to monitor stars for up to 2 months without interruption. And it's because of things like this that we're rewriting the textbooks. Now, if you're going to rewrite the textbooks, you need a pen. I have 4 pens, and they're pens that draw light curves. Very precise, ultra-precise measurements of the brightnesses of stars and exoplanets orbiting those stars. The first of these pens was MOST, a Canadian Space Agency mission. But I'm happy to announce that we're having babies. A Canadian-Austrian-Polish collaboration called BRIGHT. And the first twins were delivered last Monday aboard an Indian rocket launched into a polar orbit. And here's the launch from the Indian launch site. BRIGHT stands for Bright Target Explorer constellation because there will be at least six of these nanosats in orbit. If MOST is the size and mass of a suitcase, a BRIGHT nanosat is essentially the size and mass of an automobile battery. And although the main science is intended to study the most luminous stars in the galaxy, we will discover planets through transits. And let me put down the microphone for a moment just to show you. This is one of Canada's national newspapers, the Globe and Mail, and the Monday of the launch they ran a 2-page article about a bright constellation, including a full-scale picture of one of the bright nanosats. We live in an era where we can have pioneering satellites that you can actually fit onto a newspaper page. And feel free to check this out afterwards. I'll set it aside for people to look at. Okay. We've already done our preliminary target selection of several hundred stars brighter than magnitude 4.5. So those are the twins, but on the same rocket, not only were MOST babies, but MOST sister. The aunt to the twins, NEOSAT, Near Earth Object Surveillance Satellite. This is the first space telescope dedicated to detecting and tracking asteroids with semi-major axes less than 1 AU, and also satellites and debris in geosynchronous orbit. It's almost a twin sister to MOST, but with a large external baffle because it looks in fields with low solar elongation close to the sun, so it has to have an external baffle to restrict the stray scattered sunshine and earthshine. And on the same rocket, Canada's first military satellite. I know for many astronomers like myself, if you combine the words military and satellite, it makes you nervous. But you put the word Canadian in front of it, and it makes you feel all warm and fuzzy again. Sapphire is actually designed to do a public service. It's tracking space debris at high orbital altitude, 6,000 to 40,000 kilometers. But back to the ultra-precise photometry for planets. MOST designed, built, and operated at UBC under my supervision. Joining us in orbit 3.5 years later, the French mission, COROT, Convection, Rotation, and Planetary Transits. We always bend over backwards to make good acronyms. And that's been a very successful mission. You've seen in a few of the slides of some of the other presentations some results from COROT on some of the plots. Unfortunately, 4 months ago, COROT stopped sending signals back to Earth, and we have tried to re-establish contact with it and have not succeeded, and so it looks like the Corot mission has ended, just as we were lobbying CNES, the French space agency, to extend the very successful Corot mission. I'm a co-investigator on Corot. And nearly 7 years after most, the Americans finally got into the act with NASA's Exo-Earth Hunter, Kepler. I don't think that's the technical terminology, big sat, but Bright is a nanosat, MOST is a microsat, Corot is a small sat. At 5 metric tons, Kepler, to me, is a big sat. And so we live in an era where there are now 4 space missions, one of them just recently defunct, one which is still assembling in orbit, still has 4 more twins or sextuplets to join it. But we live in an era in which we have this kind of capability which we never had before. Why bother? Space missions generally are expensive. Even most, at $7 million US, is the cost of a major instrument on a major observatory. Well, here's an example of 3 nights of photometry studying a variable star in 2 filters from a single site on the ground, Torben Ehrentoft in Denmark data. And here's a little more than a month of photometry of a double motar Lyrae star, AQ Leo, collected by MOST, and then a blow-up of part of those data. And we can now play the game Spot the Supercomputer Simulation. One of these is a segment of the MOST light curve, and the other is a supercomputer model of what Geza Kovacs and Robert Bouchler thought that this star would do. And remarkable agreement, but even if they don't agree, the message here is we now have data whose precision and whose time sampling and whose time coverage is almost equivalent to what we produce in our computer model simulations, and that's a wonderful era in which to live. MOST was launched to do mainly seismology of sun-like stars and magnetic chemically peculiar stars, as well as Wolf-Rayet stars, precursors to supernovae. But when I was in Ensenada last year, I gave a talk describing MOST as a transformer in space. And there's SpongeBob. And it really has transformed itself. So that's our original MOST science. We've added so many things, and this is not a complete list to what we do with MOST. And what I want to tell you about for the rest of this talk is some of the exoplanetary science that we have done. Let me start with a movie. We're going to explore a system called Tau Botus. And we're going to start in Vancouver. If the movie starts, it may just be taking a while to cache. There we go. We're going to start in Vancouver at the H.R. MacMillan Space Center, our planetarium, on a sunny day in Vancouver. And we're going to race past our sun, out of the solar system, and in the direction of a star in the constellation Botes, Tau Botus. Tau Botus is a sun-like star, not quite a twin to the sun, but close enough. And we're going to zoom in to beside the planet Tau Botus b, a hot Jupiter. We're going to have to put on sunglasses so we can see the star more clearly, and we find that it has a bad complexion, and it's got star spots. But now if we look at the system as a whole over time, and this animation is shown almost to scale, just time is sped up, you can see that basically the planet is leading the star by the nose, that the concentration of spot activity is following the planet. And this was a surprise to us. The star varies at the same period as the orbital period of its hot Jupiter, and it stays in sync even after hundreds of orbits. Here are 2 phase diagrams folded at the orbital period of the planet of the star's variation taken a year apart. And if the orbital period is 3 1/3 days, that's more than 100 orbital cycles. There's work that I did with Gordon Walker, now retired, UBC Bryce Kroll. He was an undergraduate student working with us when he did that. He's going, I think he's at MIT now. I call this the tail wagging dog system. People were accustomed to the idea that stars influence planets. Not too many people have thought seriously about the idea of how planets could influence the parent star. And the only way to explain what you're seeing in the Talbota system is if the magnetic field lines of the star are tangled with the magnetosphere of this closely orbiting planet, creating activity, spots, flares, plages near the subplanetary point in the photosphere and chromosphere of the star. That is what we claimed, and other colleagues went and did spectropolarimetry to measure the magnetic field of that exoplanet hosting star, and eventually to map that magnetic field through Zeeman Doppler imaging. And here is the map, and sure enough, the magnetic field of the star is concentrated beneath the planet as we predicted. There are other examples of this that we have found and we are studying, but systems like this are one-stop shopping for science, because you're combining studying the nature of sun-like stars and stellar activity, stellar magnetism, planetary magnetism. It's just a wonderful laboratory. Now let me take you on a trip on an exoplanetary transit system. When most people hear the word transit, they think of public transportation. I'm thinking of exoplanetary transportation. You've already heard from Jillian about the WASP Transit Survey, but just to remind you, most people are familiar with eclipses, and transits are somewhat rarer, at least, and not part of the vernacular. They happen in our solar system, as you know, but from the Earth we see them only for the closer planets, Mercury and Venus. In Mercury, the last transits occurred in 1999 and 2003. The first transit of Venus in modern times occurred on the 8th of June 2004. I was in Muchhool, England when that happened, where the very first person who saw a transit, Jeremiah Horrocks, did so from his bedroom. The last transit before that was in 1882. So on the 7th of June 2004, there wasn't a single human being alive who had ever witnessed a transit of Venus with his or her own eyes. I was in a pub in Preston, England the night before. A young lady caught my eye. I was chatting with her, and at the end of the night I said, "If you come with me tonight, tomorrow I will show you something that no living human being has seen." Turned out to be a very good pickup line. Anita and I dated for 2 years, and we're still very good friends. So students out there, you never know where you're going to use your astrophysical knowledge. And the last transit of Venus was on the 5th of June 2012, and the next one, December 2117. So you've got a long wait. Don't have to wait as long if you're an alien astronomer observing transits in our own solar system. If you're outside of the solar system, you could witness transits of Jupiter and the Earth, depicted here. And in this animation, showing the kind of geometry, if you're fortunate enough to see a planetary system whose orbital plane is roughly along your line of sight, you don't get to see what is depicted in the animation above at the center, but you do see the changes in the starlight as the planet transits the disk of the star and is eclipsed by the star. But you need sufficient precision to see those effects. And even outside of transit and outside of eclipse, the planet is going through phases, just like the moon during the month in our sky. And with enough precision, and Kepler and most have that precision, you can even measure that, and allows you to study the reflectivity, the albedo of the planet, and the nature of the atmosphere, the surface of that planet. And this is really the only reliable way for us to measure the radius, the diameter of a planet. And here's a transit measured by the MOST satellite, just for good measure. You heard before lunch about the wonderful WASP program, the Wide Angle Search for Planets, and I decided to add one of the WASP targets discoveries, WASP-33, and here is the ground-based detection light curve, very shallow transit. Here is the MOST photometry of that system. We decided to observe it, and you may notice some strange wiggles in that light curve, and that's not systematic noise, that's intrinsic to the system. Andrew Collier-Cameron headed up the analysis, and basically the star, WASP-33A, is a bright, fast-spinning A5 star. It's got a hot Jupiter in an orbit only 1.22 days long, and it's a retrograde orbit. It's moving in the opposite sense to the star's rotation, only 5.5 radii, stellar radii above the photosphere of the star itself. Here are the nearly 50,000 individual measurements of our first run on WASP-33 over a little more than 3 weeks in October 2010. The star is about 8th magnitude. Here is the phase diagram at the 1.22 day period, and you see those wiggles again. And those wiggles are pulsations of the star, but plotted in phase with the orbit of the planet. And so the planet has actually excited oscillation modes in the star, likely tidally. And the main frequency is about 9.8 cycles per day with an amplitude of about a millimagnitude. There are several frequencies there, and we're doing more detailed analysis, but the star itself looks like it might be a hybrid with both delta Scuti and gamma Doradus type pulsations, and part of that hybrid nature may be induced by its planet. And here's some showing some spectral line variations. The longest spectral time series at high resolution yet obtained of the WASP-33 system. And what you're seeing in grayscale there are basically the bumps and dips in the stellar line profile, absorption line profile, induced by the pulsation. And the thing that's moving, that's slashing across, that's bright, going from basically bottom right to top left, that is the silhouette of the planet moving in the opposite sense to the wave patterns on the star in retrograde. Yeah. So we really are rewriting the textbooks on planetary astrophysics. We're also rewriting the mystery books. Mystery books are usually set in sort of dark, mysterious places. And we are exploring what are, in some sense, dark worlds. And while we're doing it, we're kind of playing poker, but not with cards, with filters. And in this game, MOST actually has the winning hand compared to the bandpasses in the Kepler, Corot, and other standard systems. It's because if you look here, here's the ratio of the thermal emission from a 1 Jupiter radius planet that you would measure through the Kepler and MOST bandpasses. And MOST bandpass basically excludes most of the thermal emission. We're really measuring the optical albedo, the reflectivity, whereas Kepler will be measuring a mixture of the optical reflection and the infrared thermal, near infrared thermal emission of the planet. Here are 3 of the dark worlds that have been observed by MOST. One of our favorites, HD 209458, and it's planet B. And here are 4 of the light curves we've assembled, and we have actually more data than these, but just on this one slide are almost 650,000 individual photometric measurements. And here is the phase diagram showing the transit and our model fit and the residuals to that model fit. Now when we model the planet through the light curve, we just don't model the planet. If you don't understand the star, you don't understand the planet. So we do a comprehensive model of the star and the planet, limb darkening, everything that we can put in. And this is showing some of the results from our model fit. And using astroseismology when available, we can even get ages. And analyzing the data that I've showed you to fit the epoch, the period, the mass of the star, the radius of the star. There we're using as well spectroscopic measurements, mass and radius of the planet, the inclination of the orbit, the bond albedo, the limb darkening, and we do Bayesian analysis. We derive a radius and a mass of the planet with incredibly small errors. Now these errors, I would argue, are underestimated, but it still shows you the kind of domain that we are now in exoplanetary science. And the albedo is probably less than 14%. This planet is about as reflective as charcoal. And that was a surprise. Jupiter, for example, has an albedo of about 50%. Then we looked at HD 189733, and here it is in a low magnification telescopic view. It's close in the sky to M27, the planetary nebula. Here are two of the light curves that we collected, and you can see it's a bit of a roller coaster, and that's because the star itself is variable. It's got major star spots, major activity. And so that presents a challenge because you have to correct for the intrinsic variations of the star, in this case that are not synchronized with the orbital period of the planet, in order to get your best fits to the transit and to the eclipse. And here is our best transit model fit, and you can see the residuals are not as good as for HD 209458 because of that. But when we apply our analysis, we find that this isn't a dark world, it's a bright world. An albedo that might be around 70%, and certainly isn't any less than about 50%. And that it may be more reflective than Jupiter. What's the difference between that and the dark world 209458b? Rayleigh scattering. The answer to that question is the same as the answer to why is the sky blue. We believe that we're seeing the first evidence of Rayleigh scattering in the atmosphere of another planet. Planets, some of the discussion at this meeting will be about planets in our solar system, including the Earth. And here is the grade 7 science textbook in my current home province of British Columbia in Canada, with a very simplistic view of the Earth's interior. We have now been discovering a category of planets we call super-Earths, for which there are no analogs in our solar system, but some of them would have interior structures that are just different in proportion to the Earth's. But there are also categories of ocean super-Earths, which would have very deep surface oceans. These models were first developed by Diana Valencia, a Canadian who was doing her PhD at Harvard, along with a colleague of mine, Dimitar Sasolov. Some of you know Dim. And she is now, I think she's still a Carl Sagan Fellow with NASA. Well, we're looking for a super-Earth. And here's our roadmap, our sky map. We put the star 55 Cancri A under the astronomical equivalent of a police stakeout for 2 weeks in February of 2011, looking for a super-Earth in a very tight orbit. There's the light curve there, the predicted times of the transit, but this would be a very shallow transit. What we were doing was gambling. It was like we were going to Vegas, playing the slot machine. First, did we bet on the right orbital period? Even if we did, there was only a 1 in 4 geometric odd that the planet would transit the star. And even if it did, we didn't know if the planet would be large enough for even most sensitivity to detect. Well, we did bet on the right orbital period, we did beat the odds, and we hit the jackpot. By folding the light curve at that suspected orbital period, we cornered the culprit. There is the transit of the planet with a depth of 1/25%. And this is what the transit would look like if you could see it, compared to the transits of Jupiter and the Earth around our own sun. And the sizes of the two stars are to scale based on our best parameters. The orbital period of this planet, 17 hours and 41 minutes. That's its year. If you lived on 55 Cancri E, you wouldn't celebrate milestones with a calendar, but with a clock. Hey honey, it's 4:59, happy anniversary. Now thanks to transits, we have a growing population of planets for which we know both mass and radius. And this isn't a complete sample, but it's representative, and Jillian showed you a similar plot before lunch. On this plot, of course, are the planets in our own solar system. And just two representative cases, Jupiter and the Earth. The curves represent very simple models of planets that would be almost entirely iron, almost entirely rock, almost entirely water, and almost entirely hydrogen gas. And not too surprisingly, you find a lot of planets, gas giants, which fall close to that curve. And there's 55 Cancri E. Let's zoom in. This planet is actually denser than the Earth, and now here are some more detailed contours, both for uniform, constant density and different compositions. But what I want to point out here is the error bars. You see some of the Kepler super-Earth systems, you see one of the Corot super-Earth systems, Gliese 1214b, but thanks to the MOST measurements and our follow-up, we probably know the characteristics of 55 Cancri E better than any of these. And here are just some of the parameters we've derived and their uncertainties. I don't think I know that many numbers about myself with that accuracy. And in fact, it's gotten to the point where we can give this planet its own passport. And it's probably illegal for me to modify a Canadian passport this way, so please don't tell anybody, at least in Canada, that I did this. 59 Cancri E is also an outlier. There is the visual magnitude, the V magnitudes of the host stars as a function of transit depth. And the host star is 4 times brighter than the next brightest star hosting a transiting planet. 100 times brighter than the next brightest star hosting a transiting super-Earth. And if you look at our stellar neighborhood, like the RECONS survey by Todd Henry and his collaborators, basically here's the census of stars within 33 light years of the Sun. And in that volume of space, 357 stars, of which 20 are G-type stars. And we heard this morning that the spectral classification of the Sun may actually be in question, but certainly in the canonical sense, only less than 24 of these stars would be like the Sun. So going back to Vegas, the odds are that 55 Cancri E is the only transiting super-Earth within 40 light years of us. There's another reason why the outlier is important. It's also important because the star is so bright that we can do other follow-up measurements. We can do optical and infrared interferometry, infrared spectroscopy. All of these things which are very difficult to do for many of the Kepler planet systems because the stars are, say, 12th magnitude. This one, we can do those things now with existing facilities, and we are doing those. In fact, my former student Diana Dragomir and I obtained spectral polarimetry with the CFHT Espidons instrument to look for the extrasolar, the star-planet coupling, because we see evidence for that kind of magnetospheric tangling. And if we can extract it from the spectral polarimetry, it would be the first detection of a magnetic field, an indirect detection, but the first detection of a magnetic field in a solid terrestrial planet outside the solar system. The other reason it's cool that it's 6th magnitude is you can see it by eye. Not the planet, but the host star. And, I grew up as a Star Trek enthusiast. It's kind of part of the occupational hazard of being an astrophysicist. And there was an episode in the original series in which Captain Kirk, played by Canadian actor William Shatner, was chatting up a young, what's her name? I've just forgotten. Joan Collins, thank you. Young Joan Collins. And basically his pickup line was pointing up and saying, see that star? There's a planet around that star that's home to one of the most romantic poets in the entire universe. I can do that now. Except I won't use it for evil purposes, but I can point up to that star, to my students, to members of the public, to journalists, and say, see that star? Around that star is a super exotic super Earth with a year only 18 hours long. And so basically, what was science fiction when I was a kid is now science fact, and I and my students and my colleagues are helping to write that real-life science fiction story. And I was worried that I might run out of time for questions. Here's an ad campaign in Vancouver for our science museum. One of the bus shelter ads. The two most common fears are clowns and heights. So there are clowns holding a net while you're waiting to drop from a great height. My fear was that I would take up too much time today, but I'm hoping that there's a little bit of time for questions and hopefully interest in it. Thank you. Muchas gracias por su atención.
Questions, comments? Please.
Hi. How do you calculate the planet albedo?
So the question is, how do we calculate the planet albedo? When we measure the eclipse of the planet, what we're measuring is first the light in the system when you have the star and the planet nearly fully illuminated, and then just the star without any scattering from the planet whatsoever. And so that tells us how much light are we losing from the planet. I should point out, by the way, the amount of light you lose during one of those eclipses is equivalent to the amount of light you lose when a mosquito goes behind a city street lamp, seen at a distance of 1,000 kilometers. So it's not an easy measurement to make. And then we can also combine it. Spitzer, the NASA Spitzer Infrared Observatory, has measured eclipses of some of these systems, including 209458, in the far infrared. And so they get brightness temperatures, which put limits on the atmospheric properties. And then our measurement, in the case of 29458, it's fortuitous that it is such a non-reflective planet, because that paints all of the atmospheric models into a very tight corner in parameter space. It's amazing how well at least we think, we know the temperature profile and the characteristics of the atmosphere of 29458b. I should point out, just before the next question too, my title was Canadian Experience Leading to Mexican Opportunities. And the message here is, think about it. We launched the first all-Canadian space astronomy satellite at a budget of $7 million 10 years ago. We now have 2 all-Canadian space astronomy missions in orbit and operating. We have another mission which is 1/3 Canadian in terms of the satellites, but all Canadian aerospace technology inspired by the science, and other missions in which we're going to extract some space astronomy, even though that wasn't their initial purpose. And so in the course of less than a decade, we had gone from being minor partners in space astronomy missions to having several of our own dedicated missions, and that's what I see in the near future for Mexican space astronomy. And on Thursday, Jueves, we're going to have a panel discussion in the afternoon, and I'd like to elaborate more on what I see as the directions for Mexican space astronomy based on the kinds of experience that we've had with Canada. We punch way above our weight class. The budget of most, $7 million US. The budget of Corot would be more on the order of $300 million. And the budget of Kepler is more on the order of $1 billion. But you can see from some of the things I showed you here, we run with the big dogs. We didn't have to put hundreds of millions of dollars on the table in order to have access to this kind of capability, and I see that as a really realistic as well as exciting opportunity for the Mexican community.
I don't quite understand why the fact that one hot Jupiter is dark and the other one is bright tells you that there is radiative fusion going on. In which planet does it? I'm sorry if I misrepresent. It's not the contrast between the two. It was just
the 219458b was the first one for which we collected these data and did the analysis, and we were surprised, as were many others at the time, that it had such a low albedo. We were expecting an albedo in the level of a few tens of percent. And if it had that albedo, we would have detected the eclipse in our first 2-week trial. And we started to set lower and lower limits. With the 1894733, even I can't remember all the telephone book numbers. In our complete model of the system, including the star, we also have corroborating observations of the planet transiting in front of spots and so on. There's Hubble Space Telescope data and so on. When we gather all of that, our best interpretation for that albedo, based on what we know about what we think is the best likely composition of the atmosphere, is that we're seeing Rayleigh scattering in order to explain it. We might be wrong, and we're still working on that. There is another system that was observed by Kepler in which they also have, the argument is seeing Rayleigh scattering. But it's not just the either or, it's not the contrast between 219458 and 189733 that makes that argument. I could go into more detail and give you some of the references afterwards, but it's not quite so simple. I apologize if I made it seem that way.
Any more questions? In the case of the planet, you mentioned that it's not, or at least connected to the star. Did you insert some spot variability for your time?
So in the Talbotis case, the first one, basically that is what we are observing, mostly spot variability. You may have noticed in those phase diagrams that the light curves look different from one epoch to the next, because the activity actually changes. The star is going through its own activity cycles. We have more data than I showed, and we're tracking it. We now also have activity proxies, chromospheric indicators, H and K photometry, and we have the spectropolarimetry. We have that for several other systems. Even 51 Pegasi, the first, nominally the first planet around a non-degenerate star to be known, we see evidence for that kind of coupling there as well. So we have a handful of systems in which we see that, and for each of them we do the spectropolarimetry follow-ups as well as other follow-ups. So everything else is consistent with activity and spot modulation, and if there weren't a planet there, and if we didn't know what the orbital period of the planet is, we'd maybe be impressed with the fact that we could see such small variations. That whole modulation due to spots is at about the level of a millimagnitude. But other than being impressed that we could see that, it would just strike us as, oh, we're seeing a spotted star with activity. But once you know the ephemeris of the planet, and we see the variations, they're in sync with the planet's orbit. We've tried every other mechanism, backheating, tidal distortion, to explain it. And the only thing that was plausible was this magnetospheric coupling. And so then going on with the magnetic mapping of the star, everything that we see is totally consistent with that model. And we're right in the process of doing that same kind of investigation for the 55 Cancri system as well. I don't know if that was a long-winded non-answer to your question. So I don't know if there's time.
Have you ever seen in your language the production of the plasma that the planet goes back to the star?
See, those are the eclipses that I'm talking about, sometimes called secondary eclipses. So that's in fact where the albedos come from, is by measuring the drop in light when the planet disappears behind the disk of the star. Oh, maybe. I thought, like I said, I apologize for the rush that I was doing. I had meant to, but maybe I thought it was in one of those slides, but maybe I got confused. I had a lot of red wine last night. Mucho vino tinto.
We got time for one final question. If you don't have
question, and that's thanks to Jaymie.
Gracias otra vez. Bueno.